Hello and welcome to another AP Physics 1 review video on something called momentum. Momentum is the measurement of mass in motion, inertia in motion. Big thing with momentum is always what we call conserved. The total momentum within a system will always remain constant. So when we look at systems, we're talking about multiple parts. When we talk about the ideas of momentum, we say momentum, which we label as P, is dependent on two things. One is the inertia, or we measure as mass, and the velocity. Okay, these two things. Because of that, momentum can sometimes have some weird units. It can have kilogram meters per second, or Newton seconds. Big thing with momentum is that it's always conserved within the system. That means that the initial amount of momentum in the system is equal to the final. That really deals with collision things, multiple objects. So what we mean by this is, if we've got two blocks, one that's coming in with this, let's say this has some mass, it has some V, and this hits a stationary block with some other mass, they're going to hit, no matter what happens, if they stick together, if they bounce off, whatever happens, the initial amount of momentum before this is going to have to be equal to the after. So what we mean by this is, one way that we can look at this is in an inelastic, meaning they stick together. If they stick together, they're going to move off together. That's one way to look at this. Another way is elastic. Elastic is they hit and they bounce off. Momentum is still going to be conserved in that case. Then there's something else called perfectly elastic, which we'll talk about in a moment. So in this case, if they hit and they stick together, which we call inelastic, that means that they're going to move together as one. Notice in this case, I now have combined masses moving. Now, I do want to say this. If I was to draw this out in terms of momentum vectors, all of this stuff here has some momentum. Even though we now have more mass moving, it is indeed still the same amount of momentum after or post collision. So what's going to happen? We may have a larger mass moving, so that means in this case it could actually be going slower. Momentum is still conserved. No matter what happens, momentum is always conserved. Now, one way this thing can happen is they hit and they stick together. Another way is that things hit and bounce off. We look at it the same way, we can analyze it the same way. We say initial amount of momentum is equal to the final. So if we have two things, let's say I've got a ball that rolls and hits something, and afterwards this one moves this way and this one moves the opposite. How can we look at this? The initial momentum of 1 plus the initial momentum of 2 is equal to the final momentum. This stuff in this unit looks kind of complicated, but you just have to analyze the individual parts. So m1 v1 naught plus m2 v2 naught is equal to m1 v1 plus m2 v2. Again, it looks a little complicated, but again, these are all the individual parts. Something we need to remember is momentum is a vector. Direction stuff matters. Not only having it happen in one plane like this, the other way is if we have something coming in and then another one bounces off and they fly off like this. Not only is momentum conserved in the x, it's also conserved in the y. So what does that mean? Let's say I have m1, m2. Post collision, m1 flies off that way, m1 flies off this way, m2 flies off this way. Let's say that this thing is initially at rest. How can we have it then that momentum is conserved? Well, at the beginning, we have some momentum this way. Post collision, after collision, it's still the same amount of momentum. How is that? Because this guy is going to have a little bit this way. You can see that's part of it. This one's going to have a little bit this way. Notice how those two vector arrows equal to what we have starting off. But notice there's motion this way. How can we make it be the same as it was at the beginning? Because momentum is a vector, right? That means that this and this are going to basically cancel. To say that the momentum of this would be equal to whatever we have at the end. Momentum is still conserved. The other thing we want to mention is in an elastic collision. In an elastic collision, the initial momentum is equal to the final, and energy is also conserved. So with that, we can use both conservation of energy and we can use conservation of momentum. If it's a 100% perfectly elastic collision. Okay? And it needs to be clearly labeled as that. Last idea that we want to talk about today is if something has indeed something called a change in momentum. If something has a change in momentum, we call it an impulse. So impulse is when we look at one object, and when we look at that one object, how that object's momentum can change. That change in momentum is due to a force in time duration. Now, when we label this, we label it as an average force, because when something gets pushed to change its momentum, it actually is pushed a little bit then harder than let up. And that time is the change in time. So this means we can find the change in momentum, meaning change in mass or change in velocity. We're looking at these ideas. We've talked a bunch in class about how this force time graph is going to look something like this. And now on this graph, the area underneath here the area under a force time graph is the change in momentum. So if we knew the area underneath there and we knew the mass, we could find the change in velocity. As always, hope you enjoyed looking at the ideas of momentum. Remember, momentum is a vector. Momentum is always, always, always conserved. If something is perfectly elastic, that means energy is also conserved. Impulse is the change in momentum of an object due to force and time. And on a force time graph, the area underneath is the change in momentum. Thanks for watching.